Hello, this is lecture 5, in which we're going to have a look at further safety analysis techniques. In this lecture, we're going to have a look at a number of safety analysis techniques with pedigree in the safety engineering domain. These analysis techniques can be found in a number of publications in healthcare, either referenced or used. We're going to have a look at failure modes and effects analysis, functional resonance analysis method, root cause analysis, and event tree analysis. Failure modes and effects analysis is widely used in safety engineering, although there are some variations on how it is applied. It investigates the effects of known failures of system elements in a system. The failures are known, and this means that a failure mode is inextricably associated with a system element. FMEA is useful to identify the degree of dependency of a service on the reliable operation of a component. The bigger the impact of the failure, the bigger the dependency of a service in that particular component. FMEA is structured by an associated method and a number of steps included in it. The results of the method are summarized in a tabular format. The steps of the method correspond to columns in that table, and while we go through the steps of the method, we populate these columns. FMEA is recommended as a team activity. The most popular application of FMEA in healthcare is the VA's FMEA, or as it's known, Healthcare FMEA. You can see the bibliography for guidance on how to apply Healthcare FMEA. Healthcare FMEA can be seen as a hybrid of failure modes, effects and criticality analysis, a variation of FMEA which we'll look at the next slides, and HAZOP. The table used to capture the FMEA results is very similar to the table used in generic deviation-based analysis techniques. Typical contents include ID, the system element under analysis, the failure mode, the effects of the failure mode, known causes, the detectability of that failure mode, control or mitigation of the failure mode, and further issues. It's worth noticing that the column about whether a failure mode is credible or not is missing. That's because FMEA is not intended for exploring unknown failures, but it is using known failures associated with a system element. Failure modes, effects, and criticality analysis is a variation of FMEA. In addition to the traditional FMEA components, it includes a severity assessment. This needs the risk level to be calculated. It is worth noting that because the failures are known, this implies that we may have evidence about their likelihood. This is easier to apply in some industries and systems than others. For example, the failure rate of an electronic component is easier to model and predict than the failure rate of a human-based function. This is an inherent limitation of the approach, and it's not caused by the method itself. Nevertheless, the method can prompt a deeper look into availability as well as the reliability of the components. Also, it allows us to evaluate whether we can have confidence in the data available about that component. Finally, during failure modes, effects, and criticality analysis, a criticality of failure mode is assigned based on risk. Using this risk assignment, a priority can also be assigned to each failure condition. This can allow stakeholders to start managing the failure conditions with the highest impact on the service. In terms of models needed to apply FMEA, known failures imply that we know the components of the service. This includes IT, components, humans, and so on. This means that we need a fairly detailed description of the system in order to understand how a known failure condition may propagate and affect the entire service. Not having a detailed model may result forcing a HAZOP, which is a more exploratory technique. It may restrict analysis in local effects, neglecting the propagation of failure conditions to the entire service. It may result in too many assumptions and risk of them of not being validated later. Finally, it may result in obscure risk control options. Given that the design of the system is not documented in detail, the same goes for the risk controls. So we may not be able to evaluate the design of the risk controls and their appropriateness for the respective failure conditions. Moving on, the functional resonance analysis method is a method commonly used in healthcare. It mainly focuses on the functions composing a service. Also, it includes the concept of resonance. That is, the interactions between functions that may cause a safety-related event. Furthermore, it captures the day-to-day operation using a functional-based viewpoint of the system. FRAM models do not necessarily need something to go wrong. So, whether a safety-related event has actually happened is irrelevant to modeling the service using FRAM. In contrast to other methods that can use any model description, FRAM uses a function-based viewpoint of the service. The function is described along with 6 of its attributes. These are the temporal requirements of the function, the input to a function, the output of a function, the resources needed by a function, the control and monitor of a function, and finally, the preconditions required for a function. FRAM considers the different variations during operation of a system. It provides a guided way of understanding variability of a system. This is expected during operation of a service, and it's quite natural in socio-technical systems. FRAM recognizes technical, human, and organizational variability. For example, a function may be late, or the precision of output of a function may be different each time the function is performed. Following identification of the functions and their attributes, we can then start building the bigger picture of the service by combining the attributes of the functions. In this example, the output of function A is used by function B. Similarly, there can be other dependencies between the different attributes of the identified functions of the service. By documenting these dependencies, we essentially capture the operation of the system in terms of these attributes. So let's have a look at how FRAM relates to the failure model that we have discussed in this course. Firstly, we can see some similarities between the concept of variation and deviation. Although the concept of variation is used in a positive context, it is compatible to the model that we have used throughout the course. Variation is considered tolerable and part of the intended operation of the system. However, this is not incompatible with the concept of deviation, as deviation has been defined as an unintended operation of the system. So in other words, if something is unintended, which is beyond the concept of variation, it is still covered by the concept of deviation that we have used all along. Furthermore, variation, similar to applying guide words to system elements, looks at changes during operation of the system from the perspective of the different attributes. Finally, upstream and downstream coupling, a concept in FRAM, is very similar to propagation of failure conditions as we have discussed in the previous unit. FRAM offers an easy and intuitive modeling framework as it is based on a concise functional view of the system. It also provides guidance through identifying variation of the service, which makes application of the framework easy and requires less expertise and training on the actual method of FRAM. However, it may miss the expressive power of other methods which use more representations of system elements and are not limited to a functional view. The graphical view is helpful, but clarity is reduced in bigger examples when the graphical view will become more complicated. And finally, it relies more on the interpretation of participants than the systematic application of guide words in identifying potential failure conditions. Root cause analysis is a very popular method in healthcare. It is a team-based exercise and it aims to identify why adverse incidents have happened by determining the underlying causes. It is usually employed to investigate the causes of an adverse effect. It identifies where we need to intervene and add controls to manage these causes. In order to apply RCA, we need to identify the incident, which will also shape the scope of the analysis, organize a team to carry out the RCA by picking the appropriate stakeholders that will be part of the team, study the work processes or the operation of the service, collect facts about what has happened and then search for causes. Following identification of causes, take action by introducing risk controls, and then finally evaluate the actions taken. These steps are not unlike the steps that we went through in the previous lecture during application of the lightweight dependability deviation analysis method. So as you can see, all these safety analysis methods have some similar principles in common. When performing RCA, we firstly need to define the problem, which most of the times will be the adverse event that has happened. Then we need to start thinking why this event has happened. This will lead us to a cause, but we don't stop there. Instead, we keep evaluating why that has happened. This will eventually lead to a series of causes until we're happy that the last cause that we have found is the root event. RCA can be a particularly useful method to health IT developers. It helps the operator of an IT system, for example a hospital, to understand how IT affects the service and whether it has been the cause of an adverse event. Furthermore, it is helpful in identifying specific aspects regarding the operation of IT and help to elicit requirements related to that IT system. For example, how human factor related issues with the IT may have become the cause of failure conditions. Furthermore, it can identify related issues. For example, maintenance insufficiency, lack of training, or support provided by the IT manufacturer. RCA is a very common tool in healthcare. It offers good returns when compared to its application cost. And it is accepted as having reduced safety adverse events. However, its application to large-scale services is limited. The results are dependent on user or team knowledge. There is a tendency to stop prematurely at most obvious cause. And often the results are not repeatable in exactly the same way. SWIFT is another technique common in system safety that may be applicable to healthcare. It is similar to HAZOP, but think of it as a zoomed-out HAZOP. It gives a much broader overview of the system as well as the failure conditions in it. It considers potential deviations to explore, and it is a more flexible technique as it doesn't need a very well-formulated model of the service. It needs a facilitator to prepare the exercise, and the information that is produced by using Swift is similar to other techniques. For example, the effects of failure conditions, controls that can be applied, etc. Swift is less exhaustive when compared with other techniques, but this can also make it more appropriate for application during earlier stages of the design of a service when the description of the service is not well defined. Event tree analysis is a method very common in safety engineering. It explores the operation of a system following an adverse event. For example, wrong prescription, overloaded A&D room, administration of wrong medication, and so on. It explores how the system can cope in the presence of an adverse event and how the success and failure of various risk controls will affect the outcome. Event tree analysis results in a list of potential outcomes which are classified according to criticality. In order to look at an example of event tree analysis, we need to consider a system and its associated risk controls. Take a few minutes to have a look at the example pathway as well as its associated risk controls in red. Each of the risk controls is intended to manage a failure that has already been identified during application of previous safety analysis. So let's have a look at how event trees are created. We start by identifying the adverse effect. In this case, a doctor enters the wrong dosage in the system. Then we try to list the risk controls associated with that adverse effect, or in other words, with that failure condition. In this example, the risk controls include an IT function performing a sanity check of the dosage, a process for the pharmacist to review the prescription, and finally, the nurse to review the prescription at a later stage. You may notice that risk controls are phrased in a positive manner. When we list the risk controls, we don't just list the functionality, but we list a specification of the correct operation of the functionality. So, for example, we do say that IT sanity check function identifies wrong dosage. The reason we do this is because during construction of the event tree, we need to ask a question with a binary answer, that is, no or yes. In other words, whether the risk control has been successful or not. Following listing of the risk controls, we then explore what will happen when the risk controls will work as intended and when they will not. By combining these two cases for all risk controls, we create a bigger tree. This tree will result in a number of outcomes based on the adverse event. Usually during application of event tree analysis, we try to evaluate the criticality of these potential outcomes. If failure of a risk control to operate as intended will result in a very critical outcome, then this risk control can be seen as being very important for the operation of the system. Event tree analysis is also a team exercise. It's an opportunity for all stakeholders to understand how a failure affects the system. This can involve clinical, IT, as well as safety staff. As with all the methods that we have seen, outcome identification is done in the context of a risk assessment framework used by an organization. Event trees demonstrate very well the importance of controls. If a control failing increases the outcome risk considerably, this particular control may be more important than others. Event risk can also be used to calculate the probability of failure of the controls themselves. Or if we can't do that, it can help to identify the need to collect this data. Moving on, as an exercise, consider any of the safety analysis techniques that you already use in your organization. If the technique that you have selected is not among the ones that we have discussed in this unit, try to identify similarities with the ones that we have. Can you identify another technique that may be more suitable for your needs? Try to justify your answer. If you are not aware of a safety analysis technique in your organization, is one covered in this lecture a potential candidate technique? Which characteristics of that technique did you find useful? Please record your answers using the relevant sheet at the end of your folder. In summary, in this lecture we have seen a number of techniques for safety analysis. All techniques have their pedigree in safety engineering and they have successful applications in healthcare. As always, you need to remember that each technique has its own relative merits and disadvantages.